All right, so we left off and we were talking about um, formal charges here. And so remember, we just said that formal charge is the group number minus the number of non-bonding electrons minus 1/2 of the shared electrons. And let's see, let me get. So we can now go to the next little bit here, just a little example for you. So as an example, what would be the formal charge on each atom here in this example? So this, of course, is an example of something that we're going to talk about later, in which this is made from a Lewis acid-base pair, which we'll talk about in Chapter 2. And so, but very quickly, here we can see that this is a Lewis base, something that has electrons to donate. And a Lewis acid accepts electrons, right? So we have two structures here that are together now via a covalent bond that's indicated here by this line. So we have covalent bond. And the two started out like this. And basically it's the reaction of these two, like so. And so this is how they would normally be. And so you can see that this one, in case, has a lone pair of electrons, so therefore it would be a Lewis base. This one has no electrons and actually has a vacant orbital, so therefore it is a Lewis acid. And so these two come together and they make what's called a Lewis acid base pair. And now what you can see from this, in this case, is that nitrogen is supposed to have a lone pair, but it in fact doesn't. The lone pair is now used here in this bond, right? So now what we need to do is figure out, well, what would be the formal charge? Well, we don't need to worry about hydrogens because they all just have one bond, right? So we're really looking at just the nitrogen that we see here and the boron. So if I'm going to look here at this nitrogen, we have, if we want to look at the bonding group here, so again, we're going to look the number of group here. So nitrogen, if you view a periodic table, right, you can get its group number. And its group number in this case would be 5, right? So then we have to subtract the number of non-bonding electrons. Well, that's 0. Right? So, and then we need to look at the number of how many bonding electrons it has, right? And so in this case, you can see that we have 4 bonds, because 3 from nitrogen or hydrogen, and 1 that's in between the two, right? So that would mean that we have a total of 8 electrons there. So for the formal charge for nitrogen, so we have formal charge is equal to bonding group 5 minus number of non-bonding 0 minus 1/2 the number of electrons that we have. So we have 4, so that's total of 8 here, right? So this brings us 5 minus 4 is plus 1. So nitrogen, then in this case, we can write it up here at the top as a plus 1 formal charge. All right, so now let's move over to the boron. So boron here, if we look at our group number, right, we can see that in this case, if we do repeat the same set of steps that are there, right, then boron is actually going to have a negative charge, So we have formal charge. Group would be 3 minus the number of non-bonding, which is 0, minus 1/2 of all of the bonds, since we have 4 here, 3, and then this one counts, so that's 4. So that is 8 right here. And so this one would give you -1. So therefore, boron in this case is a -1 formal charge. So that's just an example there of how to go about calculating formal charges. So again, just to kind of reiterate to you, this is what you can kind of learn from patterns, and you'll see this quite a bit. So basically, like I said, you won't really be going through this sort of calculation every time. You're going to more or less get to a point where you recognize it. But when you have something that's positively charged, right, you can see, for instance, in our nitrogen, notice that it has no lone pair, so it will give it a positive charge. When it's neutral, you see the lone pair that's here. Well, there was until I covered it up, right? And then if it has 2 lone pairs, therefore it's negative. So one of the big things is, of course, remembering what these should look like, so how many bonds that they should have. In a sense, what you want to do, again, is kind of follow this little hint right here. And that is that you want to do enough so that you can easily recognize it, and you don't have to kind of go through this calculation all the time. All right. So the next bit here is now what we're going to talk about are, of course, resonance structures. And resonance structures of compounds basically are something that mean we have a compound that's sort of a hybrid of all of these different resonance structures, right? So the reason for this is that basically we can say in sort of a nutshell that the structures of some compounds are not adequately represented by a single Lewis structure. Right, so basically, resonance structures are those that can be formed by moving only electrons. So you can't move sigma bonds. So a better definition would be these are, in fact, Lewis structures that can be interconverted by moving electrons only. And in particular, the electrons are either going to be non-bonding electrons or pi electrons, right? So no sigma bonds. So what this means is then, well, you have maybe 2, 3, 4 structures. So which one's real? Well, the answer is that the real structure is actually a hybrid of all of them. However, some count more than others, right? And so what you can see here in this case is that we actually have this sort of different forms of a resonance hybrid, and you can see that this is the hybrid or combined representation, right? And so notice that we have this little dotted line that's right there, and that's the one there that you can see, for instance, that indicates, okay, hey, this isn't exactly all of this. So the real structure for what you see in blue over here on the right, the combined representation, is a mixture of the two hybrid, or the two pieces here, right? The two resonance forms. So that brings into the question, well, if that's the case, and I told you that, well, some count more than others, well, how do you know? How do you know which one counts more than others? And there are a couple of things that you need to consider when you're determining that. So these are important criteria for determining which resonance structure is the most important. So criteria for determining which is most important. Number one, and basically you're saying, okay, does the structure, or this one structure, the one that is going to be the most important, would then have to say that it has as many octets as possible. The second bit of this is that this important structure would be that it has as many bonds as possible. And that kind of goes with the first one, because if you're missing a bond, then somebody's missing an octet probably, right? And then the other thing that you want to consider is, if you do have charges, then what you want to consider is where those charges are placed, right? And so, for instance, if you have something that has a negative charge, so this would be the important factor for this, is that the structure would be one that has negative charges on the most electronegative atom. Right, so that would be one that's important there. And then same thing, for the positive charge, you want it to be on the least sort of electronegative atom if it's possible. And then, of course, the other one that you can see here is that you want to have as little charge separation as possible, right? So, so these are the things that we can sort of look at when we're evaluating resonance forms. So here I have an example for you. Let's look at formaldehyde again. So the question in this molecule here is, okay, do I have a possible resonance structure? And the answer to this would be yes, because I do have pi bonds and I have lone pairs. Now, what that means is that I can actually move this guy up to the oxygen, and this would give me a different resonance structure. Now, when we're looking at resonance structures, we have a special arrow that we need to use. And this is a double-sided arrow. This indicates that we have two resonance structures, or however many that we're looking at, that are there. So, for instance, this one here. Now, I've got a negative charge up here because I moved these electrons. So this means this guy only has 3, so this would have a plus formal charge, right? So now I have something like this. Now, there's a couple of reasons that we want to consider this. Number one is reactivity. So in this case, you can see that this carbon is electron deficient. And so therefore, it would be more reactive towards something that has a lot of electrons at that carbon now because of this deficiency. And so this gives us sort of the overall true structure. The most one that we really consider is, in fact, this guy over here. But this one allows us now to include dipoles, right? So this one would have a partial positive charge, and this one would have a partial negative charge based off of this resonance structure here. However, this one, you should note, is a minor contributor to this, because in this case we're missing octet on carbon. Right, because that carbon has a plus charge. Now, I do have a question for you, and I know that you can't answer me because this is a video, but you can answer me in your head there. And notice how I drew this arrow up top from this one. So I have this guy. I didn't draw in my lone pairs that were there. And we said that we can move non-bonding electrons or pi electrons. And so those pi electrons are things that are involved in a double bond from a pi bond, right? And then, of course, non-bonding electrons are your lone pairs. Why can't I just have a resonance structure where I move this down here? The answer lies in that there is no space on this carbon to hold another bond. This would be implying that now you would have 3 bonds on the oxygen and 5 bonds on the carbon. That is impossible. Carbon can only have 4 bonds, so there's no place for that to go. So that means that drawing a resonance structure, in this case from this one like this, is absolutely out of the question. Right? There is nowhere for that to go. Right? So the only way that you can draw a resonance structure there, in this case for this molecule, formaldehyde, is by pushing the electrons up to the oxygen and removing them from the carbon, which gives you that minor contributor over there. All right, so let's look at another example here for these, because resonance structures are important. We can now look at, for instance, something like this. So in this case, if I were to put in all my electrons, you would see that oxygen, remember we said oxygen needs to have 2 bonds. It has an extra electron here, right? So it's a negative charge there. Is there potentially a resonance structure that I could draw? Well, remember, I need to have something that has pi bonds. And so over here we have a triple bond, and so this is composed of pi bonds, right? A sigma bond and 2 pi bonds. So here I have pi bonds. So I can move those. So what I could do potentially here is take 1 pair of these electrons to give me another bond, which would do this guy over here. But notice that I have 1, 2, 3, 4 bonds already around this carbon, right? So I have to be able to move that. Well, I can, because I can move a pi bond, and I can move this electrons from this bond to the nitrogen. So this, maybe you see there. If I add in my electrons from this one, remember I already had these 2 here. Now I have these guys, which would give it now a negative charge, 2 bonds to that carbon there on the other side, and now I have these 2 lone pairs. So then the question becomes, all right then, which one of these is the major contributor? Well, you answer that by saying, all right, I need to look at my charges. Which is more electronegative? And we're looking at the ones that have the negative charge on them. So on this side over here, I see that I have oxygen that has a negative charge, and then the other one on the right, nitrogen, has a negative charge. Oxygen is more electronegative than nitrogen. So this means that the favored contributor is the structure on the left. And that's because oxygen has the negative charge. right? So, so in this case, then the one that we really like here, does this work? Oh yeah, is this guy right here. Right, this is the favored. And again, it's because of this. All right, so there are some times when you may have opposite charges and things like this. They need to actually be on adjacent atoms. And so here's an example of what I mean by this. And these are, you can kind of group these into what we call non-equivalent resonance. So for instance, in this case, if I have a molecule that looks like this, and actually I should redraw this a little bit different for you, so it might make a little more sense. Remember that the bond's coming from the carbon, so I have these guys like this, right? And so here, notice I can't move any of these. These are all sigma bonds, so those can't be moved. I do have some lone pairs here, right, that I can mess with. The other one here, note that I can't move these this way because that carbon already has a full octet, so there's nowhere for those electrons to go, so I have to move them to the right. And if I move them to the right like so, then that means I've got to break a bond here, and so that would push these out over here. So this would give you a resonance structure that looks like this. And now I'm just going to redraw this. Let's draw it this way. Oops. Like so. And notice again, if we're adding in all of our electrons, I have now 6 that are not bonded on this one. And I just have the 1 here because I used one of these to move in, right, to make a double bond. So this means that this guy now would have a plus charge because that oxygen has 3 bonds. And so it turns out that these two resonance structures are really not equivalent at all because this one has no charges, right? So, and it doesn't matter that even though this one has a negative charge on an oxygen over here, right, it's still not the best thing. So in the long run here, the biggest sort of important aspect of this is that the most stable resonance structure is, in these cases, the one with the smallest separation of oppositely charged atoms. Okay, so now that we've kind of gone through some of that, let's look at some examples. So what we want to do here is draw the important resonance forms for this molecule that's right over here. And there is indeed a positive charge on it. And what we want to do in this case is we want to indicate which structure is the major and minor contributor or whether they have the same energy. So The first thing, of course, that you want to do when you're solving these problems is correctly draw the structure out. So what I would like for you to do is pause the video and make sure that you can draw the structure out, and then see if you can come up with the right answers here. So give it a pause and give it a try here and see what you come up with. Now, if you're going to do badly here and not pause the video, the way that we're going to start this, of course, is by looking at the condensed structure that I have here. And so we'll talk about that coming up here in just a couple of slides. So what you can see from this guy is, if I'm looking over here at this CH3, I see that I have a carbon that has 3 hydrogens. So I'm going to put hydrogen over here. And it's directly attached to an oxygen. And then this guy is attached to a carbon that has 2 hydrogens. So this means that I have a carbon with only 3 bonds, and that would give it a plus formal charge. All right, so now I need to draw a resonance structure of this. Well, in this case, what you want to do is fill in your lone pairs. And I have 2, of course, on the oxygen. So I can, in fact, draw a resonance structure by moving one of these sets of lone pairs over to form a new bond, which gives you this structure. And now moves the formal positive charge from that carbon to the oxygen now that's over here. So now the question becomes, well, which one is the major contributor and which one's the minor? So there's a trick to this one. Now remember, I know I told you that you want negative charges on the most negative atom and things like that, but we have a positive charge here, and notice that in the first structure, right, that we have a carbon that doesn't have a full octet. So in this case, this one is going to be the major contributor. So why would that be? Well, basically this means that everything here, everyone on this case has a full octet. So this one would then be the minor, and the reason for this is that all full octets. And that was one of the big rules that we had at the beginning. So again, so the fact that this one has complete octets makes this the most important resonance structure. Another example would be to draw the resonance contributors with the compound below, right? And so again, we want to look for things like pi bonds and that type of stuff to where we can move these electrons, right? So again, you should kind of pause the video here and see what you can come up with. So in this case, we're looking at these electrons that are right here, this negative charge. And what we're going to do is we're going to move this guy over. So because I have a pi bond here, that means that I can move it, right? So I'm going to move this to form a bond between these two, which then causes me to have to move another bond. So making a bond makes you break a bond over here, right? Because I can't have over 4 bonds on carbon because I have 1, 2, 3, 4 already on this carbon. So I've got to do something, and that means I've got to move it. So then I'm going to move this guy up. So that gives you now a new contributor. That looks like this. And what you can see now is that we have 2 different resonance structures, right? So which one should be major and which one should be minor? Well, in this case, basically what you can see is that everything has an octet, so we're past the whole thing, which one does or doesn't have an octet. Everyone does, right? That means they have the right amount of electrons there. So now we need to look at charges, and what we can see is, in fact, that in the one over here on this one, the negative charge is on the oxygen. That's important there, right? The negative charge being on the more electronegative atom, which is oxygen. And so over here, the negative charge is on a carbon, so that's not good. So that means that this one would be the major contributor, while this one is the minor. So you kind of need to work through those sort of rules. One of the biggest things, though, of course, is checking for octets. Right? Make sure everything has a full octet there. So the next thing that we're going to talk about, and that I briefly mentioned to you, are structures and structural formulas and such. And so that we have a better understanding of what we're talking about, what we're going to do is kind of go over those. So, of course, this Lewis structure is one that you're commonly know most about now. But you can see it's kind of a pain having to draw all of these things out all the time. So in the case of these and drawing these types of deals, we're basically going to draw these or write these out without showing the bonds. So you need to sort of understand that it is implied that the bonds are there. And you typically are going to list to do it 100% correctly. Sometimes we'll make exceptions because we're trying to show something in a specific way. But for the most part, you're going to list central atoms and then things that are bonded to that central atom right after it. So, for instance, in this case, you can see that in ethene over here. Let's do that. We have ethane. That's this molecule with 2 carbons. And we're going to list the carbon first, and then it has CH3 around it all the way around here, so this CH3, but we're going to write CH3. Now the thing that you have to remember is this is telling you that these hydrogens are actually around the carbon over here, and that the carbon itself is actually bound to the other carbon here in this area. Right, it's not attached, this carbon is not attached to these hydrogens, so that's one thing that you want to kind of remember. And there are other ways that we can do this as well, depending on what the structure is. We can add things like parentheses, subscripts, and all that kind of stuff. So let me just give you some more examples as to how you might do this. In this case, a condensed formula for the bromine that's here with this structure. Notice that the easiest thing that you want to do is count your carbons. So we have numbers that are right here. So carbon 1, 2, 3, and 4. Right. So I'm going to count 1, 2, 3, and 4 to make sure that I have the bromine on carbon 3. Right. So this is sort of one way to do this. The other way, when you have multiple bonds, is to, in fact, show the multiple bond out here. Notice the alcohol that I have. That's this guy, this OH group. That's an alcohol functional group. It's on carbon 1. That's right there. And notice that I have carbon, but I have the OH to the outside of this, right? So this is a way that you would want to do this, because we also have hydrogens. So I need to imply that, okay, I have OHs and hydrogens. So one has to go to the other side or it begins to look a little funky. The other thing that you may see is if we draw it like this, we have HOCH2, and then I have CH2. You may also see CO and then CH3. Right? Now, if you look at that, this is telling you that in this case, without writing the bond out, notice that you have, of course, the only way for this to have an octet is to have a doubly bound oxygen here. Right, so this and this guy are representing the same thing. Right, so you want to just sort of make sure that you kind of get the hang of some of these. More or less, they're shorthand because most of the time you're not going to see a structure drawn out like this. It'll in fact be drawn out like this over here in this condensed formula. And then we even actually have a more, I guess, lazy way of doing it when we look at these sort of line angle drawings. So here are just some examples for you. I don't think I need to necessarily go and do all of them, but what I wanted to point out for you here is notice that this carbon right here in the center, right, this has a CH, and then there are 3 CH3s coming off of it on this side, right? So the CH is that, right? And so we have 3 of the same group, so we're going to put a parentheses around it. And notice that we have CH3, but we have 3 of them, so we need to put this parentheses and then put a subscript with 3 there to indicate that we, of course, have 3 of them, right? You can also do this when you have numerous repeat units, right? So notice that I have 1, 2, 3, 4 CH2s. Well, instead of writing out CH2, 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 the way that you would do this is start here, and you would write, of course, CH3, right? But then you're going to group all of these together, and so you put CH2 in parentheses, as is shown right here, with 4 of them because we have 4, right? So, and so you just need to kind of go through and look at these different structures here and different ways of writing it. There are some that have multiple ways, like for instance, this one over here, right? So there are multiple ways of doing this. This, I guess you would kind of say, is the most common here. And so basically, whatever the laziest way you can think of, that's it. Notice that it's indicating because you have 2 of the same groups, right? The ethyl groups here with 2 carbons on either side, so it's typically going to be written like that. So I just want you to kind of go through and familiarize yourself with these. There's really not a whole lot that I can do except for just tell you to look at it and sort of understand what they are. Also, looking at multiple bonds, one thing that I want to point out to you is notice here, multiple bond not shown, multiple bond not shown, right? Multiple bond here not shown, right? So this is the common way that you're going to see it. And so you need to remember and understand that, yes, this carbon needs to have 4 bonds, so there definitely have to be 3 bonds in between that carbon and nitrogen, because also the nitrogen has to have 3 bonds. Notice what also isn't shown. Lone pairs, right? So lone pairs are omitted, right? So we typically don't show lone pairs there either. Now, most of the time when you're an organic, you're really not wanting to draw out a carbon itself. So instead, we use a line, and every point that a line intersects with another line is implied to be a carbon. So yes, we're getting even lazier. So for example, here we can look at some line drawing. So what I'm going to do is I'm going to just sort of give you a compound. So we can just look at, for instance, butane. So we'll just draw it out in the typical Lewis structure fashion. And then so if I want to convert this to condensed, it would look like, and then I have 2 of these guys here. Right, so that would be my condensed version that you can see. So now there's an even lazier way to do it, and that is to just use lines. So if I were to say, all right, carbon to carbon to carbon to carbon, right, like this, which would imply that this carbon is here. So you would then, add the hydrogens all the way around. Well, now you know that it needs to have a full octet, right? So this one would have, for instance, hydrogen, hydrogen, hydrogen. So it's the same here. I just drew it with some little kinks in it here, right? And so now the even lazier way, or the line angle drawing, is to actually draw this. And what this is equivalent to this. So here what you can see is that at every point you have a carbon, and it's implied that all the hydrogens are there, right? So if you see a line drawing like this, this is telling you all the necessary hydrogens that should be there. It's implied that they are in fact there. So this one basically is implying that all necessary H's are present, right? So this is telling you that everything that should be there is in fact there, okay? Now, when do you need to put in bonds and things like that? Well, there's some rules for this, and so you kind of want to get familiar with it because this is the most common way that you're going to see things represented in this course and in any other organic thing that you do or anything that you see. For instance, if you look at the structure of a drug that someone may take, like, for instance, Sudafed, which we'll talk about later, it's going to be represented by line drawings, right? And so here are some sort of examples. Let me go in this case. And so a couple of things that I want to point out to you. Notice what's depicted here. So atoms other than carbon must be shown. And then, of course, double and triple bonds must be shown, right? So those must also then be shown there. So anything that's not carbon, you have to show it. Even with hydrogens, if you have a heteroatom, remember we talked about those other than carbon, right? Those heteroatoms, you need to add the hydrogens onto those too, okay? So there are two rules with this, and that is that if it's something besides carbon, make sure that you show it, and if it has a multiple bond, you have to show that too, okay? Remember, that's different in the condensed structure. You don't always have to show the multiple bonds. Now, another thing that's important that kind of goes with this, and this reason we covered this line drawing here so that we can draw these effectively, but is that we've talked about resonance, but then there's something else that we need to talk about. And what we need to talk about now is something called pKa. All right? And so what I'm going to do here is I'm going to insert a slide really quickly. Get a blank one. And we're going to talk about pKa here very briefly. We'll get some more into this a little bit later. pKa, which is the negative log of the Ka, right? And so what is Ka? Well, for any reaction, let's just say Ha goes to, let's say we put it in water. So water goes to H3O plus A minus, right? And so the Ka that you would get is equal to the products over the reactants, right? And so water, of course, is equally on both sides, so we can ignore it. So here, if you remember from Gen Chem, H3O plus and A minus divided by the reactant, okay? So here we have this Ka value. Well, it turns out that Ka values are usually huge, long numbers, right? Like 1 times 10 to the minus something, 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 right? And so what we don't want to do is often have to write all of that. So what we do is use the negative log of that, and it makes it a nice, simple whole number for us to evaluate, right? Or a nice, simple number without scientific notation. So, for instance, if you're looking at HCl, and we put this in water, see, I kind of did a little trick on you, OH2, and then H2O. We get, of course, H3O plus Cl minus, with water being everywhere, so we can kind of ignore it. Right, so the Ka of this is 1 times 10 to the 7, right? So that means that it completely dissociates, right? So we get that because pretty much nothing is here. All of it is dissociated to this. Well, then what we need to do is convert this to the negative log. And so the pKa is equal to -7, right? And so this tells me that it's really acidic. So the thing to remember is lower pKa is more acidic, right? So the lower the pKa, the more acidic. Now, resonance has a direct impact on this acidity. And let's change this. I don't know why this is the way it is, but we're going to ignore this. What is here? I have somehow messed up the slide, so we'll ignore that. And it turns out that if we look at something like this versus something like this. So we're looking at which hydrogen is the most acidic. And in this case, we have an alcohol, this one, and in this case, we have what's called a carboxylic acid. That is this whole big piece. That's called a carboxylic acid.
Do you understand the words that are coming out of my mouth?
So if we're looking at an acid-base reaction, then what this means is that, of course, we're looking at the most acidic proton, and it would be this OH versus this OH that's over here. So if I were to take some base, and I'll just represent it with this guy, and deprotonate this, then the conjugate base that I would have for this would be something like this, right? Versus this guy with some base. And this would give me this conjugate base. So the question becomes, which one is easier to do, right? Which would then sort of mean which one is the most acidic. So if I look at this guy over here on this side, what I see is that all of the negative charge that is here, of course, it's on an electronegative atom, oxygen, but it's all situated right there. Right? This one on the other side, though, notice that I have a negative charge here, but I have a pi system that's right here. So here I have the ability to do some resonance. So I can actually draw a resonance structure by moving these guys in and then these guys out. So what this means is that I can look at this in a different way. I sort of have that minus charge that's spread between the two of these, right? So it's spread between this oxygen and this oxygen. So you can think of this in terms of holding a hot potato, right? So if you, let's say, make a baked potato and you go to grab it right from the oven, or if you do microwave, right from the microwave, and you don't have a glove to help you with the heat, what's going to happen? Well, it's going to burn your hand, right? So if you were to take that potato and then toss it in between your right hand and your left hand, now it probably would burn each hand a little bit, but then it wouldn't just be sitting on one single hand, right? And so it's the same sort of scenario here for this guy. Notice that I have two oxygens that can actually take that negative charge. In one case, it's on the one on the bottom, and on the other case, it's on the one at the top. If you look at the guy over here on the left with the red circle around it, then what you'll note is that there is nowhere else for that charge to go, right? And so remember, when we talk about pKa value, the lower the pKa, the more acidic. And so for that reason, the pKa of ethanol is roughly 16, right? And then the pKa of acetic acid is roughly 5. And that is because of this, the resonance that you can draw for that. Right? So resonance can have an effect on acidity, and it really deals with, and this is the key aspect to this whole discussion on this, is the stability of the conjugate base. So basically that means that if you can spread charge around, think of the hot potato analogy, then it's more stable because it's less likely to get burned in one spot. All right, so now we're going to briefly jump in here, and this will be the end of the first video. After we discuss this, we're going to skip empirical formulas for now, and we're going to move into some bonding here. And so I just have a quick little life lesson here for you. Detail about bonding, and the things that we're going to talk about, we're going to discuss in more detail here: wave properties, electrons, and basically accounting, for what is actually between the bonds that we're looking at. And so, chemistry is pretty much emulates life, right? And so you can think about chemistry as, sort of the meaning behind life in this. That's a little much, but you get the point. So life is all about chemistry, and of course life is all about meeting people and therefore making and breaking bonds. And so as an example, how your life changes after you get married, right? So before marriage, you have the picture here on the left, which is wonderful, and then after you get married, this is what is reality, right? So and that's pretty much chemistry. We're looking at how things change after bonds are made and or broken, right? So this is has nothing to do with personal experience, just FYI. So let's look at our first set here. We kind of already talked a little bit about this, and we're looking here now at wave properties of electrons. So remember that standing waves or a standing wave vibrates in a fixed location, right? And so therefore, basically, we have what we call this sort of wave function, which is a mathematical description of a lot of different properties of this, and they include things like size, shape, and of course orientation. And therefore the amplitude can either be positive or negative. So, the top piece there. So we can have plus or minus, just as you see here. So we can have a plus or we can have a minus, right? And then, of course, we also have the sort of center there in the middle, which we refer to as a nodal plane, which we've already discussed. And it's this guy right here. That's your node, right? So it turns out that this is how we describe where electrons are, and this is basically how we get the sort of orbitals that we refer to. So this wave function over here is represented by our p orbital that you can see in this case, and so basically you would kind of just sort of imagine that this guy goes like this, and so here is your p orbital, like so, which is represented by this, all right? And so So this is how we get these plus and minus sides and these different orientations and all of this stuff here. Now, where this comes into play mostly is going to be how we sort of put things together and make bonds, because the wave function is going to describe the orbital that the electrons are in that is making said bond that we're talking about. Okay, and so for this one, we're going to go ahead and end the first video. We'll have one more video here for this chapter, and then we will start on chapter 2 as well. So thank you very much for your attention, and I hope that this was helpful for you. Of course, you can always remember that I will be available to answer questions on Thursday. I believe it's August 30th. So I will be available for that. And you can, of course, you can always email me as well. So thanks again for watching, and I hope you found this helpful. And I will post another video very soon.